All right, hey peeps. I'm just showing you the textbook here because of questions 4 and 8 to answer, and they're mostly kind of verbal. I was thinking of just doing a video of myself, but my hair's gross. Number 4, page 384, says, in sports stadiums, an activity called the wave is sometimes performed by the crowd. Is this a true mechanical wave? If not, what compromises are being made with respect to the definitions given in this section? Okay, so talking about definition, let's start with that. A mechanical wave. Mechanical wave. Can you see that? Yeah, you can. Mechanical wave, the transfer of energy through a material due to vibration. Vibration is the cyclical motion of an object about an equilibrium point. So there's issues with both of those parts. In a, if I have a pendulum, pretend this is like hanging down, blank, 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 blank. The energy goes through it. This is the equilibrium point. Goes this way, goes this way, goes this way, goes this way, right? With a wave, like at a stadium, shouldn't use pencil, you're not going to see that. If you have somebody, here's like the side view, so here's the bench. Clearly that's a person ready to do the wave, vectors for hands. Okay, so anyways, they're going to jump up. So they jump up and vectors, they do this kind of thing, right? And then they sit down. The equilibrium point, there's all kinds of issues with this, but the equilibrium point, where is it, right? This is at rest, this is fully extended, which means the equilibrium point should be somewhere in there. And a mechanical wave kind of does both, right? The other thing to think of, oh, marker on the textbook, poop. Oh yeah, mechanical wave, where is that? Transfer of energy through a material due to vibration. It's not like, so it's the transfer of energy through a material. It's not like everybody's connected and somebody kind of punches this guy in the shoulder and he pops up and he hits the next guy and they hit the next guy, like boom, 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 kind of a thing, right? Energy's coming from inside. So when it asks what compromises are being made, with those definitions, you have an issue with the vibrations, not around an equilibrium point, and it's also not a transfer of energy through a material. Cool? That was number 4. I'm going to fold this in case I write on it again so it doesn't go in the textbook. What was the other question? 8. Provide 2 examples of a complex wave motion. Describe the wave motions and explain how you know that transverse and longitudinal waves are present. 2 example complex waves. So complex wave has transverse and longitudinal, right? Remember the difference between those two? So transverse and longitudinal has both. Think of, the very first thing I thought of is if you were to like jump into like a pool or the lake or whatever. You go down into it, so 3-dimensionally. So let's say this is the surface of the water. So you cannonball into that thing. You're going to create disturbances going down this way, and you're also going to create disturbances going this way. Okay? Just try and think of it in 2 planes. If you have like a sheet hanging on the clothesline, do you guys even know what that is? Like, do you sincerely? People used to, before they had dryers, or could afford them or fit them in their apartments or houses or whatever, they would hang clothes out on a clothesline to dry. So imagine you have a sheet hanging, and if you punch that sheet, it's going to kind of billow forward and back. Like if you're looking down on it, it'll kind of do this a little bit, but it's also going to kind of do this, right? It's similar, very similar to the water, except now imagine it vertically. Does that make sense? Goes in lots of directions? I hope so. All right, bye.